Okay, let's look at a particularly sort of more advanced differentiation question that you might get in an exam. So let's see what we've got here. You've got a curve. You've been given the function definition for it as an algebraic expression, y is a function of x. You're going to have to find its derivative, so that should be fine. Find the minimum point, making use of the previous part. Find an equation of the normal going through the 0.16. Remember, the normal is the line which is perpendicular to the tangent, and that should all be within the realm of possibility for you guys at the moment. Perhaps part triple I, you want to try and think of how can I most efficiently get that answer. And then part B, you're looking for the integral of this particular function, which happens to be the curve function. And for B double I, you're then going to use this to find the area under this curve between 1 and 4, wherever they may lie. Obviously not between, say, 0 and 4, because that wouldn't be possible, because this function is not defined when x is 0, is it? Because you've got a division by x squared. So we can't divide by 0, therefore there's actually a vertical asymptote here, although it's not shown on the graph. Okay, so therefore it makes sense that they would ask for the area between 1 and 4, and not between, say, 0 and 4. Okay, so have a go at that question. Hopefully you do okay with it, and when you're done, we can take a look at the working and check our work. Pause the video now. Okay, so we've got the following function, x plus 1 plus 4 over x squared. I'm going to change that to 4 times x to the minus 2, same thing. And therefore, the derivative will be, well, x derivative is 1, the derivative of 1 is 0, and the derivative of 4x to the minus 2 will be, I've written plus now, but really should be minus. So multiply 4 by minus 2, get minus 8, x to the power of, take 1 off the power. Okay, so finally we have this, 1 minus 8 x to the minus 3, that's the derivative. That's part I done. Then part double I, the curve C has a minimum point M, find the coordinates of M. So as you know, to find minimum points, we want to set the derivative to be 0. Okay, so the minimum x, or I should say the minimum point, has the x coordinate which satisfies this equation. So let's see what we'll get here. That implies 1 minus 8 x to the minus 3 equals 0. And with a bit of rearranging, we get this. So I multiplied both sides by x cubed there to get 8 equals x cubed. And if 8 equals x cubed, that implies, well, x must be equal to 2. And only 2 in the case of a cubic. Because if it was minus 2, you'd get minus 8 when you cubed it. So x is 2 and only 2. Okay. However, we want the coordinates of M, so we're going to have to take that 2, and we're going to have to say, well, M is equal to 2, and then what? Well, that's going to be the value of y, the original curve, and I plug 2 back into here. 2 plus 1 plus 4 over 2 squared. Hopefully we can see that comes out to be 2 plus 1 plus 1. So we get 4. Okay, so M is equal to 2, 4. Okay, and that's II done. Cool. Let's get rid of this working then, just leave the rest there. For then part triple I, we want to find an equation of the normal to C at that point. Okay, so imagine there can only be one line. If I just go back for a moment, you could imagine perhaps, well, if that's the minimum there, so that's technically when x is 2, isn't it? So that is at 2. So you can already see 1 is going to be about here. And then if I were to draw the normal, might as well just draw it roughly. That's a bit too rough. Hang on. I'll get it. Third time's the try. There we go. Third time's the charm. Okay, so that's about normal. Okay, because that should be about 90 degrees there. So we're effectively finding the equation of this line. Okay, and we can see there will only be one such line, and it apparently crosses at 1,6. Okay, so let's then think about how we're going to do that. So if we find the tangent gradient when x equals 1, let's see what that would be. So dy over dx when x equals 1, or let's write that the other way around. When x equals 1, dy dx is equal to 1 minus 8 is minus 7. Okay, so if we go back, we're effectively saying the tangent of the graph at that point has or the gradient, sorry, at that point is about minus 7. Looks about right, doesn't it? Because negative number gives me a gradient which slopes from top left to bottom right, and it's quite steep. Minus 7 seems about right. So therefore, if that's minus 7, then the blue line is going to be the negative reciprocal of minus 7. So the negative reciprocal of minus 7 is 1 over 7. That's the negative reciprocal. So in other words, flipping the fraction times minus 1. Okay, so this is the gradient of the normal of that blue line. Okay, then we're going to make use of this particular form of the line equation. Okay, so not y equals mx plus c. We're going to use this one. You can use y equals mx plus c, but personally I find it's good to get in the habit of using this form, because this is the form you should use whenever you know the gradient and you know a single point that it passes through. Okay, so we're going to have y minus, now in this case y naught refers to the y coordinate of the point that it passes through is 6, m is the gradient, is a 7th, and x naught is the coordinate of the point it goes through, specifically the x coordinate, that's 1. Okay, so that, I mean, technically that is in some sense a final answer, because that is an equation which describes the line, but we'll just neaten it up slightly. I'm going to multiply by 7 both sides, and then I'll add the 42. Okay, and at this point I would say that is done. Okay, I know it's not in the form y equals mx plus c, but as I said, that is just one possible way of expressing a line equation. So, you could change this to y equals a 7th x plus 41 over 7. You could, and it would still be correct, but there's no need. This is good enough as a final answer, and it looks simpler than dividing the whole thing through by 7. Okay, so that's our normal equation to see at the point 1,6. Cool. Right, so let's look at finding the integral of this function here. So we've got integral of x plus 1 plus 4x to the minus 2 dx. That will be a half x squared plus x minus 4x to the minus 1. Okay, and you can always check by doing the derivative of these and seeing if you in fact get this. And then a plus c. Right, so that's I done. And then II is asking us to then find the area of the region bounded by the curve C, the lines x equals 1 and x equals 4. So if I go back to the graph, remember the lines x equals 1 and x equals 4, I mean, they're just going to be that line there, x equals 1, and x equals 4 is presumably about there. So that's the x equals 1 line, that's the x equals 4 line, and we're being asked to find that, if you can see it, that yellow sort of area under the graph between the x-axis, between the two red lines. Okay, so what that is simply finding the integral with the limits 1 and 4. So let's do that. The integral from 1 to 4 of this. So now it's a definite integral, which is the same as the indefinite integral, except we don't need to put a plus c, but instead we have to put the limits on the outside of our expression like this, and then substitute in. So let's substitute in 4 first. A half times 4 squared plus 4 minus, and then this I'll just do immediately. 4 times, this is 1 over 4, will just be 1. Okay, so that's the left hand substitution there. Yeah, that makes sense. And then let's take away a half times 1 squared is a half, plus 1 minus, and in this case we just have 4. Okay, so that's this whole thing here, a half 4 squared, that's just 8, plus 4 is 12, minus 1 is 11. A half plus 1 minus 4, that's the same as a half minus 3, which is a half minus 3 minus 6 over 2, so that's minus 5 over 2, I think, huh? So minus 5 over 2. So that's going to be 11 plus 5 over 2. That's 22 over 2 plus 5 over 2 equals 27 over 2. 13.5. Okay, and that's our answer. That is the area under the graph, 13.5.